dash 8, 3, 4, 4, 4, 5, 5, 5, 6, 6, 7, 8, 9, and B, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and C, we have 2, 3, 3, 1, 2, 3 of those, 1, 2, 3, and then 3 of those, and then 6, 6, 7. And for D, I'll do 3, 5, 6, 7, 7, 8, 8, 8, 9, 9, 9, 10. And then for E, 1, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 6. All right. So sketch a dot plot. Which shape best describes this data? Okay. So a dot plot. Dot plot is where we have basically on the bottom we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have a dot at 3, 3 at 4, 3 at 5, 2 at 6, 1 at 7, 1 at 8, 1 at 9. Oh, that's such a fancy dot plot. No applause, just throw money. Then down here, I'm going to do 1, 2, 3, 4, 5. So I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then down here, we have 1, 2, 3, 4, 5, 6, 7. And so I have a 2, 2 3s, 1, 2, 3, 1, 2, 3, 1, 2, and 1. And then let's pause there. All right. So if I were to start trying to describe things on these, this appears on there. Hello. We're on the 1-8. You got it. So I would say this appears just by my artistic ability that it's skew right. Okay, can you see a tail pulling to the right? I hope. This one appears to be rectangular. This one appears pretty close to being normal. Someone might say that it could even be bimodal because the 4 and 5 happens the exact same number of times. But usually a bimodal, it's like the ends of it have humps on it, but you could get away with it, so it's easy to argue that one. Can I move off this screen? Please. Pretty please, sugar on top. All right, then we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I have a 3, a 5, a 6, a 7, 7, 8, 8, 8, 9, 9, 9, 10. And I would say this one, because that's off the left, I'd say skew left. And again, you might be able to get away with saying it could be bimodal because the 8 and the 9 have the same number of points. But again, bimodal often, if you were to look at the picture, would look something like this. Okay, but if you said bimodal, I'm not going to. I think it's a good argument to say, yeah, it's this because of this justification. Oh, is it okay to move off that? And then letter E. I got 1, 2, 3, 4, 5, 6. I got a 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 1. This appears to be pretty normal. Okay. Again, some of you might be able to argue that bimodal might be a good idea on that. Okay. So is there any question about, yeah?
Does it for bimodal require like a valley? That's what it's saying.
Yeah, usually a valley, but here's how you could kind of argue that and probably be able to justify it, especially in here. You could say, well, there's an infinite amount of numbers between 3 and 4, decimals. So you could make that kind of argument, and it'd be pretty hard for me to say, no, I think you're wrong. So, I mean, if you didn't put bimodal, if you said it's normal and didn't put bimodal, you're correct. I would hope that you would at least say it looks normal, and then you might, if you wanted to add to it, say it could be bimodal, but
Could it not be bimodal if it was discrete data though?
yeah, I like that too. So here's the key on that. On our words up there, it says that we have this data. It didn't say it's discrete though.
Okay.
So that's kind of a clue too. A lot of times in statistics, it's like, what exactly did it say? Well, it didn't say that it was discrete. So those are all fine arguments. I mean, I know sometimes it becomes a little nitpicky on it, but you know, it just gets, that's the beautiful thing about this class is you can easily, you know, hey, I can justify this and this is why. And I'll be like, okay. All right. Bimodal distribution, create data set, that would be bimodal. Okay. You could pretty easily, this is just one of many. You could have, say, like 2, 2, 2, 3, 4, 5, 6, 6, 6. That would totally be bimodal because you'd have 2, 3, 4, 5, 6. So 1, 2, 3, 1, 1, 1, 1, 2, 3, something like that. So that's definitely bimodal. That's definitely not normal. But that's just an example. You might have any number of examples that are probably 100% correct as well. All right. Then number 3 says, study each situation, decide the shape it is likely to form. The number of runs scored each game by a baseball team. Baseball players in the back, or is it elsewhere too? What's kind of a score of a baseball game that, not the obscure one. What do you usually see? Like ballparking it.
Like
8-6.
8-6.
You don't get like 147-3. Is there a mercy rule in baseball?
Yeah. Depends on what you need.
Oh, I gotcha. So, number of runs scored in by a baseball team. So a baseball team, you could have 0, right? You're probably not going to win. But then, you know, how far does this number go out? I mean, I would say like if you saw up to 10 runs, that's probably a pretty active game. But this could definitely be more than 10. So this type of thing, you would have stuff like this. You'd have a bunch of 1s. You might have a couple 0s, 2s, a bunch of those, 3s. Probably 3, 4, 5, 6, maybe 7 or 8. Might have about the same. But then you have that one game that you whooped them by 21. Okay? I mean, that's not as likely to happen. I know we got some good hitters in Creek One State this past year, which is fantastic. But this is kind of a big-time outlier. So I would say if you start looking at things where you could have an outlier, I would definitely think baseball, you're going to have runs between 0, maybe up to 10 with the obscure. So this would be a skew right because you could have an outlier out there. It doesn't mean you did. It just means that you could. The high temperature each summer day in Denver. Okay, high temperature. So Denver summers probably range anywhere from, you know, we could have that one kind of cold day where you're actually putting a light jacket on up to probably 105. So I figure our data probably looks something like this. Something like that. So you might be able to get away with normal, but let's face it, we've had snow in June. So you might have that way down here situation. Okay? Okay, this is that one cold day, and this might create a skew left. Now, I'm not saying it always happens, but we've all lived here long enough. So you probably, I don't know if you follow this rule, but I bet you your parents and or grandparents who live here do. Trunk of the car, you still with me? You got stuff for below 0 temperatures to, okay, if it's kind of freezing, above freezing. You probably have 2 or 3 jackets in your car, sweatshirts, just because you don't know because you live here. But those are some things. So I'd say temperatures in Denver could be skew left with the summer. And then the last digit of the Social Security number. So Social Security number, the last digit could be 0 through 9. And it doesn't mean there's more zeros than nines or any other number. I would say this would totally be rectangular. Okay, rectangular would be a good one to fathom on that. Because again, just because my last digit is a 3, and I bet you have some of you that your last digit is a 3, but I bet you all have all the other numbers in there as well. So rectangular. The smaller your data sets, though, the smaller your data set, the more it will start looking. It could lead you to thinking a different shape. So, like, let's say, just out of something being obscure in here, if I asked all of you, well, who's the last digit of your Social Security number, there happen to be more 9s than anything else. Does that mean that because there's more 9s, that 9's more likely to happen, or is it just because we are a small enough sample that we might just have more 9s? I mean, if I took a sample of 100,000 people, or 200,000 people, or 1 million people, I bet you we're going to get really close to that rectangular. Okay? What date?
Angry Birds, yeah.
Okay. Describe this data in terms of center, spread, and outliers. Create. So describe the data set. Well, number 8. Never mind. I have to plug that into Desmos, don't I? Sorry, I was still talking about. All right, I was in meetings for way too long yesterday, so I've kind of lost my mind a bit. All right, we're going to our friends, the Desmos. All right, I can't do that. Will somebody kindly please read me that data set? Doesn't matter if you go top to bottom or across. Right, 28's first one. 38, second one. 29. 45. 63. 42. 38. 36. 28. 34. 72. 37. 51. 32. 26. 44. 37. 45. 34. 58. 65. And 40. And you said there was a 72 in there? Is that right? Or did I? Okay. I just make sure I didn't flip-flop it. All right. Create the appropriate data display. Which type of data is this to you? Provide. Okay. So I could take this data and create a histogram, because we've worked with histograms. Histogram of X1, and hit the little plus. Okay, and maybe we'll change our bar width to 2. Nope. How about 3? Nope. How about 4? How about 5? 1, 2, 3, 4, 5, 6, 7, 8, 9. That one's okay. That one looks okay.
Wait, would a stem plot work for a data display?
It could. I'm just seeing if it changes too much. Again, we're making this based on our person. So this actually might be a really good one to take a look at. Okay. So this appears to be a skew right. I would say that 72 is making it skew right. Hey, why did I change the widths when all of the others seem to work? Who am I trying to impress with my data? It's whoever's reading your stuff. So this shows skew right pretty easily, but if I change this to 5, that might be showing a skew right. If I change it to 6, that could be a skew right as well. Those all work, and it's just a matter of your preference and what you want to do. The reason it's skew right is because that if I drew that normal curve in there, it would definitely be pulling to the right. What do you anticipate between the mean and the median? If it's skew right, remember the mean is pulled the direction of skewness. So that means that the mean is going to be on the right side of the median. The middle of the data will be to the left of it. The mean will be a larger number than the median because the mean is influenced by the skewness. Okay? Does that vocabulary kind of make sense? And you could easily figure out the mean and median if it asks you to. And then it says, calculate the standard deviation. Well, we could do the long, drawn-out method, or we could just say, hey, Desmos, STDEV of x1, it's that. And just in case you weren't sure how just by looking at it, we'd see the mean and the median. Bless you. All right. So the data I have up there, standard deviation is 12.7. The mean is 41.9. The median is 38. So, hey, take a look at our actual mean is. Mean is 41. Is 41 a larger number than 38? This week, I think so. That's where the skewness, where it's going to pull it to the right. Okay. So, the standard deviation in the context of this problem, if you were to write out the vocabulary for it, the standard deviation means basically the majority of my data would fit, well, if you want to make it 100% like statistics, 68% of all of my data would fit between 41.91 plus or minus 12.7. 68% of my data would fit between 41.91 and 12.7. That's basically how you put it in context. That's kind of a newer way to think about it. I wouldn't give you a quiz at this very second and be like, hey, what was that? All right. Yeah. Yeah. All right, let's go to 1-9 in the notes. Yeah.
Where did you get 68 from? That's 30.
Oh, so a standard deviation is how the average distance away from the mean, which one standard deviation from the mean to the right and left is 68% under a normal distribution. But that's like next chapter, so I'm kind of like a little bonus for you. All right. We just did 1.8, right? So this is 1.9. All right. Box plots. Box plots. Sometimes they call them box and whiskers. Okay? They are a way of looking at data. Box plots very easily find you skewness. Write this down on the notes someplace where you can see it. A box plot you can't find the mean. The mean doesn't exist on a box plot. Yes, you could use technology like Desmos to find you the mean if you're plugging in a data set. But if you were just given a box plot, you would not know what the mean would be. The only thing you can tell up here on this graph is because this tail is showing that it's going to be skew left. That would mean that our mean would be to the left of the median because the mean is pulled in the direction of the outliers or the skewness. Okay, this is skew left because this rectangle is the same size, but this is a longer tail. It means I got some outliers out here. So my median, if I were looking at this graph, would be probably below 69-ish, roughly. Okay, so that's one way of looking at it. All right, so let's talk about how these box plots work and what you're looking at when you're actually taking information. All right. So a box plot, and let's even include this, let's call this an outlier. Nope, I'll call an outlier on the other side because that's where our skewness is. Okay, so the very middle of this rectangle is the median. This over here is Q3. This over here is Q1. That means quartile. This is your lower extreme, so the end of it. Notice I didn't highlight the outlier there. This is our upper extreme. And things about this type of graph does this. 25% of my data fits right there in the middle. Okay? 25% of my data fits down here as well. 25% goes here. Now, a debate in the world of statistics, which I know this is such a cool statistics. Well, why doesn't
Oh my god.
Oh my God, dude.
Because I have to use phone for
Dude. All right. So the big debate with a bunch of statisticians, which is probably like the most boring debate you'd ever come across, is does this outlier count as part of this 25%? And I kid you not, about half the statisticians say yes, and about half say no. So what's the answer? I have no idea. It's kind of like the last presidential poll I saw. Let's actually talk about presidential poll real quick. Okay, because I know we've all been subjected to it, and I'm not too concerned who you think you should vote for or who should win. But this is just a little side note. I'm not saying these are the initials of any particular candidates in the political race. So you might see a poll say something like this. Have you ever seen something that kind of looks like that? Okay, so that plus or minus 3%, it could be plus or minus whatever percent you want. This is called the margin of error. Do you want to know what this poll, if you were looking at this poll, do you want to know what this poll means? They have no freaking idea who's leading. And the reason, and this is just what I had just seen the other day. So this means that this person with an initial T could get between 44% and 50% of the vote. This person, initial H, could get between 45% and 51%. Okay? Being that these ranges here, 44 to 50, 45 to 51, overlap, like if you had them drawn, they overlap each other, that just means the margin of error is like, it's too close to call. We have no idea. Okay? So why do we look at polls? Maybe they're showing polls to try and impact people, to get people out to vote. I don't know. I mean, please, my little social studies thing for you is your vote. If you are voting in this next election, don't let somebody tell you that your vote doesn't matter. Vote every time. Yeah.
Just because H on their range is a bit higher, would that mean that they're like statistically more likely?
Here's the hard thing. You have to read that little tiny small print that's always at the very, very bottom of the screen. That's like 0.1 font. Even if you have like the 100-inch TV, you still can't read it because it's so small. You want to know how they collected their data. Okay, and I kid you not, like some of the polls, like they might be a poll, you know, a guy standing out here in front of King Supers, asking people who they're going to vote for, collecting data that way. That is not a random distribution, and it's a horrible way to collect data. Or they might say, oh, we called everybody who had an iPhone. Well, not everyone has an iPhone. So you have to, that little small print, if you ever can get your eyes good enough that you can see that small print, you'll look and see exactly how they collect the data. The keywords you're looking for, random sample, and from where. We took a random sample from Colorado. Well, if I take a random sample from Colorado, it's great, it's taking a random sample.
But I can't take a random sample from Colorado and apply it to the rest of the United States. I mean, I know we're Colorado's really cool, but I don't want them to take a random sample of Tennessee and it applies to us.
No.
Tennessee ain't cool.
I like this.
So,
So I just know this is something that we'll work on further, but I just want, because we have all been subjected to seeing some sort of polling numbers, political ads, all these other kind of things. This basically means they have no idea. They can't make a prediction based on these poll numbers of who they think would win. Even though one person has a higher starting percent than the other, because of the margin of error, this margin of error, the terminology that they would use here is they might say, they could make a conclusion based on this if it was truly done as a truly statistical way of a random sample where everyone had the same probability of being chosen. They could say, we could say with 90% certainty that if we ran our statistics again in the exact same way, collecting the data the exact same way in the exact same time frames and all that kind of stuff, that we are 90% certain that we would fall within that margin of error again. And again, it doesn't lead to one. Statistics will not predict a winner. Statistics will give you a ballpark thought of how the data was collected on who could win or who doesn't win, or who's leading and who doesn't lead, but that's kind of it, yeah.
How do they come up with the margin of error of that exact number?
Okay, so that's going to be about February, which is too late, but I can tell you, if I'm going to create a statistical study, okay, I want to create myself a confidence interval. I want my confidence interval to be anything.
Okay, so confidence interval works like this. Let's color all the area under this curve. Okay, and let's say this is way far this way, and this part is way far this way, where somewhere in the middle of this is the mean. Okay, so do you agree with me, just by my incredible artwork, is that green a big portion of that normal looking curve? Okay, so this study might be a 99.9% confidence interval, whereas if I did this, that's a small area, right? The confidence interval on this, we are 51% confident. And that confidence interval means, so the bottom one would mean I would be 51% confident that I were to collect the data again in the exact same way, that I would fall within that colored region on the bottom. Whereas on top, I could say if I did a confidence interval, if I did collecting data again and my confidence interval was really wide, then I feel 99.9% sure that my data would fall somewhere amongst there. So sometimes the confidence interval, like people see a 99.9, think, dude, that's incredible. They know what they're talking about. No, a 99.9% is like you have no idea where your data is going to lie, so you're making it as wide as possible. So like, let's say we were to take ACT scores. Let's say the average ACT score here at Cherry Creek High School was a 25. I'm making this up. I don't know off the top of my head. I'm sorry. So let's say everything's being taught the same teachers, students had the same education coming up. Principal Silva might come to a statistics person and say, hey, how likely is it that we would fall within the same average score on the ACT next year? And we could say, well, what do you want your confidence? Well, I want to be so confident. Well, you want a 99.9% confidence? Yeah. Okay, I'm 99% confident that our scores will fall between a 25 plus or minus 10. So that means all the way down to 15, all the way up to 35, which is capturing a huge amount of people. So the confidence interval, it's kind of a reverse thought. Honestly, if you look at the lower confidence interval and someone were to capture that again in that little area, their data, that would be like, holy cow, this means something. Whereas the big confidence interval, yeah, of course. If I wanted to say I want to figure out the average height of people in this class and what would the probability that the next person came in fell within plus or minus 3 standard deviations, which encompasses 99.96% of the population, I could say I'm 99.96% sure. My confidence interval is 99.96% sure that if I had the next person walk in this classroom, that they would fall within 3 standard deviations of the height, average height in this class.
So the confidence, the bigger it is, it's just, so yeah, you're more confident if your range is wider.
You're more confident that you're going to fall within that,
Okay.
which means think about like 99.96.
Yeah.
That is really close to 100%, right? If you've got a 99.96% on a test, you're not really worried about the 0.04% that you missed, right? So you're really confident that it's going to fall within that huge range. So it's kind of it's a weird way to start thinking, because you're going to start realizing, especially once we get done with this class, that statisticians, they're just sitting there playing the system, and they look at the general public, who is not us, because y'all got blessed to have me as a teacher. We're smart. The general public's dumb. The general public is, oh yeah, look at that. That must be good. It's like, no, it's not good. I kid you not. There's, it's a Friday. I can give you a side note story, because I know you guys hate those. I lived in Vegas for years. I used to my math coordinator. She was engaged at the time, and she's now married. He was one of the higher ups at the MGM casino. At the time, that was the largest casino in the world back in the 90s. Largest hotel casino in the world. So she says to me after my second week teaching, hey, let's go to the MGM tonight. And I'm like, all right. And I'm thinking, I don't really want to gamble, especially at the MGM. Like, their table minimum at the MGM is like $10 on a Friday night. I mean, I want to go to the dollar table so my money lasts longer. So I give back $1 at a time versus $10 at a time. And she goes, trust me, you're going to love this. So we walk in. I meet her fiance. He takes us to this back room, gives us $20,000 in chips. No money has come out of my pocket. He's just given me $20,000 in chips. Gives Gail $20,000 in chips. I said, okay, here's the rules. You can drink any sodas you want. You can drink waters. You can drink juice. No alcohol. Okay. You can tip the dealers. Okay. You can gamble on anything you want. If you run out of chips, come find me. I'll get you another rack of $20,000 in chips. Our job was to go out to the tables to create excitement at the tables, so people walking by going, oh, that's a good table, so they'd come down and lose their own money. I got to learn how to play every game in Vegas. The dealers had no idea that they call these people clams, like, seafood clam. They call those clams. And it was so fun. But there's times I'd be at the craps table, and people are like, oh, I'm going to bet on the field bet, which is 2, 3, 4, 9, 10, 11, 12. If any of those numbers come up, you win. Okay? And people are like, oh my gosh, look at all these numbers. It's like a 50-50 shot. It's like, no, it's 41% probability you're going to hit in there, because it doesn't incorporate the 6, 7, 8, which has a higher probability of happening than any of those numbers. And so I'd be trying to teach people, going, your statistics is wrong. And I'd be sitting there and I'd pull out a little piece of paper, look, this is how it works. And they're like, oh. So no, it's still 50%. It's like, you're an idiot. And then I'd watch them lose money, and I'd sit there. But it was fun. I'd sit there. I was learning how to play the games. I learned everything about craps, baccarat, blackjack. I even got called on because I was really good at counting cards. And so I'm playing with their money. So it's legal to count cards as long as you don't improve your bet when the odds are in your favor. So I was doing like these $10 bets. And all of a sudden I'm at a plus 16, which gives me about a 4.5% advantage over the house. So I changed my $10 bet to a $500 bet and won. So Pit Boss comes over. So you're at a plus 16, weren't you? Yeah. do not change that bet. Count all you want, but we're also counting. We know what you're doing. Sorry. So I almost got kicked out of the casino with their own money. So is there anything else I have to teach here? Or do we just finish this up? No, why don't we finish this up on, what's that day coming after Sunday? Monday. Sound good?
Yeah.
Everybody happy?